Okay, it's not quite 11:30. Okay, anyway, thank you, Antoine. So I'm going to continue discussion of quantum black holes today. But actually, as you'll see, it's mostly about the SYK model and the close connection between certain types of black holes and the SYK model. But I'll begin by just showing you some slides from colloquia I've given so that you just get a general idea of the big picture of the idea of holography that's very common in string theory and quantum gravity, and how this is a new and in some ways very interesting incarnation of a more general idea of holography. The interesting thing about this new realization is that it's much more tractable. This is a case where both sides of the holographic duality can be understood. In all other instances, only one side can be understood of the duality. And so that's led to a lot of progress in recent years. Anyway, so what I showed you yesterday was the Bekenstein-Hawking calculation for a Schwarzian black hole, which is a generic black hole of mass m, with asymptotically Minkowski space in 3+1 space-time dimensions. So it presumably describes many objects out in the universe. And the important results of Bekenstein and Hawking were the Hawking temperature, which had precisely this value, and the entropy, which is proportional to the area divided by the Planck length squared, and a factor of 1/4. So I gave you the derivation of this. Really, that is the derivation that I presented yesterday of these results. So these results have some remarkable features. First of all, the entropy is finite, so you might have expected that quantum gravity is full of all kinds of divergences. In fact, in quantum field theory, if you compute analogous quantities, you get an infinite answer. But in quantum gravity, somehow, it seems to have a finite number of degrees of freedom. The other is, unlike any other quantum system we've encountered before in statistical mechanics, it's not proportional to the volume of the system, but the area. Okay. So, given these features, one thought you might have, and people like Tuft and Susskind had these thoughts a while back. Let's make a quantum computer. This is how I would restate what they said. Given, we want to make a quantum simulation of a black hole. They didn't use those words, of course. So a quantum simulation of black holes must have some qubits. How many qubits should it have? Well, it must be proportional to the surface area. So these qubits are going to form a hologram and faithfully reproduce all the properties of the black hole. And it's a hologram because you're projecting from 3 dimensions to 2 dimensions. There's a dimensional reduction without loss of information. That's what a hologram is. Okay. All right. So now, but now you can ask, what kind of computer should it be? How should the qubits interact with each other? Well, now we need to know another very interesting property of black holes. If you solve Einstein's equations to a perturbed black hole, so you have a black hole we know is a static solution, which is spherically symmetric, but you perturb it, say by throwing a star into it or something. Well, you can then continue to solve Einstein's equation and look at the shape of the black hole, and you'll find that it comes back to rest at a perfect sphere, but with a slightly larger mass, of course. And then you can ask, how long does it take to come to rest in a perfect sphere? What is the relaxation time? So this was computed in 1970, and it turns out to be this number, 8 pi gm over c cubed. And so now we just notice a simple numerical coincidence that this is actually just h bar over the Hawking temperature. So from the point of view of the quantum computer, whatever the qubits are doing, they better have Planckian dynamics that I think Antoine has introduced before. So that's a very important constraint. And in fact, this constraint was very much on my mind when I started thinking about the connection between SYK model and black holes, because that has exactly this type of dynamics. I just curiously mentioned a paper in Physics Letters last year where they took a lot of LIGO data of the merger time of binary black holes, the last stages of the merger, and they, from the data, they deduced also the value of the Hawking temperature, just using Hawking's formula, and they find that this merger time is pretty close to the Planckian time. Okay, this is not a surprise. This is just a test of classical general relativity, but it's kind of cute how you see the Planckian time observed in observations. They haven't seen any quantum effects, I hasten to add. All right, so therefore our quantum computer should not only have a number of qubits proportional to the surface area, it should also have very strong interactions between the qubits so that it has Planckian time dynamics. All right, so that's one general way to think about it. And so what are systems that have Planckian time dynamics, which are then sitting on the surface? Well, the systems that have been studied in string theory are conformal field theories, and this is the ADS-CFT duality. So from this point of view, a conformal field theory in 2+1 or 3+1 or higher dimensions is just some quantum system which has Planckian time dynamics. And that at least makes it a candidate to be dual to certain types of black holes. And indeed, in some cases, with a lot of supersymmetry, you can indeed show that duality. But you end up with a conformal field theory that it's really, in that case, more of a postulate checked in by some limiting cases. Because the conformal field theory itself you can't solve. It's just so strongly coupled in general that the only way you deduce its properties is by computing the properties of the black hole, which turn out to be simple Einstein equations then. I mean, there's a lot of evidence the postulate is true, but the details of the conformal field theory you cannot independently work out. Okay, so question? So the question is, can you make life simple? Well, as I mentioned yesterday, you want to make life simple by looking at a charged black hole. So take a solution of Maxwell's equations and Einstein's equation in a black hole with a net charge. And then what you find if you're falling into the black hole, that your universe becomes two-dimensional. Only one space and one time. Directions I call zeta and tau. And the angular direction x can be ignored for the most part in the low energy theory. So if that's correct, then coming down to, and you can just focus on one space and one time dimension, and if holography is still applied, well, then this should be dual to a quantum computer in 0 space dimension, because you go down from 1 to 0, okay? So you want a quantum computer in 0 space dimensions, which has Planckian time dynamics, okay? And that's, of course, the SYK model. So this is just a very general way of saying, of guessing that there might be a connection. Okay, so, all right, so that's just a very general introduction. And what I'm going to now show you, that there's actually a much deeper connection, and some of the equations that describe the dynamics of black holes and the SYK model are in fact exactly the same. And unlike the usual ADS-CFT duality, we can work on both sides of the duality, on the black hole side and the SYK side, and really compute quantities and check that they match. So, and that's not been possible before in other instances of holography. Okay, well, okay, these are just slides I made for a colloquium, and saying the same thing again. There's a duality between SYK models and some of its strange properties to a dual set of variables that describes charged black holes. Okay. All right, so let's get down to something more definite rather than the colloquium-style pictures now. Okay. So let me just summarize here. I'm going to make a table of things that you have already seen some of it. And then I'll also mention in this table things we're going to hopefully see by the end of this lecture. So what Antoine showed you in his lecture last week was the SYK model has an extensive entropy in the zero temperature limit. Here we're taking, of course, the n goes to infinity limit before we take the zero temperature limit. And this is associated with these exponentially dense levels that Antoine just showed you. So, and Antoine gave you a computation of the number S naught. What we're going to see today is that there's a correction here which is linear in temperature. And so this, I'm going to focus on understanding why this KBT is here, as about half my lecture will be deriving this term. Okay, but let's take it as given. On the other hand, for a charged black hole in 3 space and 1 time dimensions, I give you all the equations on the board. You just do some algebra with those equations, and you can deduce the low temperature limit of the entropy at fixed charge Q. You can get, in fact, the entire expression, not just the low temperature limit. It has some complicated temperature dependence. You take the low temperature limit, you get a zero temperature answer. So A0 here is the area of the horizon at zero temperature. And then you also get a term that's linear in temperature, which is also expressed only in terms of A0. And there's a 1 over G out front here, which is the analog of the N out front here. Okay, so this is the leading low temperature answer. Really, it's already implicit in the original Gibbons-Hawking paper, this result. Okay. And okay. So in 2010, I didn't know this, but I knew that, and I said, okay, maybe there's something here. Yeah.
Can I think of n as the number of patches I need to cover my black hole surface with the Planck squares?
Yeah, I mean, it's some combination of A naught and also 1 over G. It's A naught over G, yeah, if you wish. Yeah, you could. Right. Yeah, you could do that, although I think a better view is to just take N as the analog of 1 over G. And A naught is just a parameter that describes the black hole. Yeah, it's the only parameter you need. It's somehow determined by the charge of the black hole. Okay. All right, so then you can try to do something else. So one of the things that also Antoine showed you last week, you can compute the Green's function of a fermion in the SYK model. And he showed it had this general conformal form, 1 over sine pi t tau, with some scaling dimension delta, which happens to be 1/4, and an exponential factor that determines the particle hole asymmetry. Okay, so in the case of a black hole, you can also compute a Green's function. What is this Green's function? This is just a free fermion moving the black hole background. So you have a ADS2 metric. So you have a metric which is ds squared is d zeta squared plus d tau squared over zeta squared. That's ADS2. And you take an action for a fermion, and it'll be d2x, the square root of the metric, some psi bar, some gamma psi. You have to couple a Dirac fermion to ADS2. There's a certain way of doing it with a spin connection. I don't remember any of that stuff. And you solve this, and you compute the Green's function of this fermion on the boundary of ADS2. So this had been done, actually, in 2009, maybe 2008, by John McGreevy, Hong Liu, and Nabil Iqbal, and Tom Faulkner, and others at MIT, who were trying to, at that time, looking at various duals of what happens when you take a conformal field theory and you add a charge to it. And that also leads to, very naturally, to the consideration of ADS2 fermions. So I dug up their answer, and here it is. And it's exactly the same form. And what we noticed here that this form, as Antoine showed, is due to conformal invariance. And this is also due to conformal invariance. Here, the conformal invariance is the SL2R symmetry of ADS2 that I mentioned last time. So the SL2R is, in fact, isomorphic to the conformal group in one space and one time dimensions. Anyway, okay, well, I'm going to go into that conformal invariance in much more detail today. All right, so these exactly match. And as Antoine mentioned, this E right now is an arbitrary parameter. The factor of 2 pi has been chosen so that this E turns out to be the electric field right on the surface of the black hole. Okay. But right now you can just say, okay, let's define this parameter here, E, for the Green's function of a fermion with unit charge moving on the surface of a black hole. Okay. So that fixes E. You just take a fermion with unit charge, and you'll get exactly this form here from the electric field that's on the surface of a black hole. Okay. So then you can ask, how does the entropy, this S naught, depend upon the charge? And this is the particle-hole asymmetry that Antoine showed. And that entropy depends on the charge. This ds dq is 2 pi e. And you derived that relation, right? So that was key to the Luttinger relation that Antoine established. So here, what you do is you just take the equation of state of the black hole that I gave you last time. I wrote all these equations on the board that came from the Gibbons-Hawking term. Gives you entropy as a function of charge. You can also work out the electric field from the expression on the board I had last time. Play around with it, and you get exactly the same result. Okay. So all of these connections were convinced me that I was onto something, even in 2010, but no one paid any attention. Anyway, but fortunately in 2015, Kitaev did something more. He showed that this connection is even deeper and even stronger. And then, of course, everyone started working on it. What he computed, and this is what I'm going to describe now, are the corrections to this. So this is on the SYK side, this is the correction I'm going to now discuss and outline how this is obtained. It's minus 3/2. The 3/2 is a universal number, and it's related, the 3 is related to the fact that SL2R is a 3-dimensional group, a non-compact group. And it's a log of 1 over temperature with some constants. And you get exactly the same corrections also for black holes. So the derivation of these two is the main purpose of my lecture today, at least to outline the derivation of all the steps that goes into this. And then once you know the 1 over n corrections to the entropy, or the order G0 corrections to the entropy here, you can invert these results to obtain the many-body density of states. So this is, of course, simply follows from the formula that the partition function is the free energy over temperature, which is the integral over d of e to the minus e over t. And then the entropy you define to be minus df dt. So given the entropy as a function of temperature, you can do an inverse Laplace transform and get d of e. In this case, you need to know more than just the 1 over this leading term. And there's some very sophisticated arguments given by Witten and Stanford that show you that you can actually do the inversion essentially exactly at low energies. And that's where you get this result here. So it has the same dependence on energy. This is the Hawking entropy here. This is the GPS entropy here. And this has a gamma, which is the gamma over here. And here, this quantity is also the gamma that's over there. So it's essentially the same form. And I'm going to try to give you some understanding of what these results mean today. Okay. All right, so that's a rather ambitious plan, but let's see. But now you know the main results. If I don't get to the end, maybe next time I'll see a few more things. Actually, before I go ahead, let me since Antoine just discussed this, let me show you at least one limit of this result that makes a lot of sense. So you'll see why, at least some of it. So the claim is that the many-body density of states, let's just stick to the SYK model, which is what I'm going to stick to for the next, is e to the n s naught times sinh. This is proportional to sinh of square root of 2n gamma e. Okay, so let's focus on the regime where the argument of the sinh is very large. So you want square root of 2n gamma e to be much, much greater than 1. So the energy is about 1 over n or even bigger. Then this is e to the n s naught plus square root of 2n gamma e. Is there a 1/2 somewhere there? Huh? No, this is fine. Okay, overall 1/2. Okay, and this is actually a very familiar result because you can get this from the fact we know that in the microcanonical ensemble, the many-body density of state is just e to the s of e. So that's all in a microcanonical ensemble. Now, in the canonical ensemble, we've learned that S of t is n s naught, is n times s naught plus gamma t. So this tells us that the free energy is some ground state energy minus n minus n times s naught t minus gamma t squared over 2. I think that's plus. So if you now take the temperature derivative of the free energy, you'll get the entropy. And then from this, you also know this is E minus Ts. So now that gives you E. And if I remember this right, you'll get E is E naught plus 1/2 gamma t squared times n. This is very simple algebra. This is really thermodynamics 101. And so now you express S in terms of E, and therefore the S of E will be n s naught plus square root of 2n gamma E minus E naught. Okay, so the fact that it goes like this in this regime is exactly what you would expect it just from thermodynamics. Okay, the square root of E is a direct consequence of the linear temperature dependence, which I haven't established yet. So the only new thing here is the sinh, the fact that there's another term here, so that when this becomes very small, it vanishes as the square root of E. So this tells us also that d of E, as E goes to E0, the ground state energy, is E to the n s naught times square root of E. And this square root is very closely connected to the square root of E at the end of the Wigner semicircle density of states that Antoine just showed you. There he was just diagonalizing a random matrix. Here we have no random matrix, we have a many-body system, but right at the bottom of the band, it seems to have a similar behavior. But notice there's a huge factor out front that was not present in the Wigner ensemble that Antoine mentioned. Okay. All right, so let's do some calculations to try to understand where all of this comes from and why black holes have the same behavior. And in fact, this is probably this formula has been known for a while by many people, but I think this is probably the first time I'm showing it expressed in this form in terms of the area of the black hole. You notice that there's h bar squared here and only an h bar here, so this is very much a quantum correction to the Hawking result. Okay. Oh yeah, and one more thing. Yeah, so this is the plot that Antoine just showed you for the SYK model, and so this behavior here fits the behavior all the way down to zero energy, and there's presumably a square root cusp at the very bottom. But to contrast with what the string theory realizations of black holes, and there are a few cases, starting the work of Strominger and Waffa, where they have computed, counted the states of a black hole using a string theory, but those rely heavily on supersymmetry. That allows you to count the low energy states, but in fact what they're counting are zero energy states. So the density of states in supersymmetric string theory is very different. It's got a delta function, and really truly violates the third law of thermodynamics because of supersymmetry. There's no such delta function in a generic black hole. So in that sense, this SYK is closer to reality than string theory, at least at low energies. And all of the string theory solutions are also for charged black holes. There is no solution where you can explicitly count the states for a neutral black hole, even in string theory. Okay, all right, so let me go to the simplest thing here. Before you go to any fancy stuff, suppose I was, just a poor condensed matter theorist, and I was trying to use condensed matter tools to figure out what is the leading correction to the entropy in the SYK model. All right. Okay, so that's what I'm going to discuss now. And do it while using the language of conformal perturbation theory. Okay, so which is something that now should be familiar to most condensed matter theorists. So the idea is that we've solved the SYK model and got this conformal solution. We found the Green's function. Let me call it G star, and I'll stick to the particle hole symmetric case is sine of tau over square root of tau. And this is valid for the SYK model for tau much, much bigger than 1 over u. Or j, what did you call it? U? Yeah, so let's stick to u. Okay, so that's the low energy answer, and it has scale invariance, but it also has conformal invariance, as we'll see in a few minutes. So let's assume that your action is some stationary action S star, which gives you this. And say we are interested in now the corrections to this. Okay, so this is the leading answer. So we can write G is G star times 1 plus dot, dot, dot. So we want to understand what are the corrections that are going to appear here at shorter times. At very long time, this is still the correct answer, provided the time doesn't become as large as n. But so I should also say that it's much, much smaller than n times 1 over u. So in this regime. So n has gone to infinity, so we won't worry about this for now. But anyway, it's useful to keep that in mind. So in this regime, when n has gone to infinity, we want to know what are the corrections here. So this is the subject of corrections to scaling, well-established theory in theory of critical phenomena. And the best way to think about it is that all of these corrections are due to so-called irrelevant operators. They're higher dimension operators, and this basic operator, the fermion operator, mixes with those higher dimension operators, and each higher dimension operator gives you a correction. So those higher dimension operators could be viewed as corrections to the fixed point action. There's some fixed point action, which gives you this Green's function exactly. After you do some RG, you decompose the microscopic action to the fixed point action plus some corrections. And the corrections I'll write in the following manner is lambda h times some operator O sub h of tau, which you're going to integrate from 0 to beta. And so these are some operators. They have to be bosonic operators because they're in the action. And I write them as a sum over some real numbers h. And the real number h is defined by the following requirement that if I compute the correlation function of this operator in the fixed point action in S star, that's going to give me some quantity that decays as 1 over tau to the 2h. So there are some other operators, higher dimension operators, that will appear in our RG. And they usually, as we'll see, they're basically some linear combination of fermion bilinears and various time derivatives of the fermions. So these operators are designed so that they have a power law decay with some exponent h. Okay, so these would be what you call primary operators in conformal field theory. So there's some tower of operators h. Unlike usual conformal field theories, we'll see that h has an infinite set of values here. If you look at the Ising model, has some fixed point theory, and it has an energy operator, and it has a spin operator, and that's it, pretty much. So that's because it's a rational conformal field theory. All the scaling dimensions are rational, and they terminate at a certain point. This one is not like that. H, in general, will be irrational. And all the possible values of H, in fact, are now known. And I'll show you how they're obtained. OK, so now the point is, so this tells you if I do scaling analysis. So my scaling analysis, just tau goes to tau over S. You do rescaling like this. And so that tells me the dimension of tau, we say, is -1. Then the dimension of OH under rescaling is just H. So that's the definition of H. There's some set of operators with arbitrary dimensions. So for the Ising model, you'd put the energy operator here and all descendants of the energy operator, which are just, so it's very simple, this kind of expansion. In fact, it's just free fermion, so that's all there is to it. This is not free fermion. And so we want to determine what these operators are. And once we have these operators, we can then figure out, we can do conformal perturbation theory. So what I do is I take my original Green's function, so my Green's function, which is g, schematically there's some integral over psi. It's psi. You have a psi over here. And you have exponential of S star plus sum over lambda, sum over h, lambda h, OH. So if I drop this, I'm now just going to expand the right-hand side in powers of lambda h. So this will give me g star plus, again, very schematically, sum over h lambda h times the 3-point correlator of OH psi psi in the fixed point theory. So now this, in general, is complicated to evaluate, but we can figure out what power of tau it's going to give me in this expansion. So g of tau will be g star of tau plus some correction. Well, I can estimate the correction very easily. Well, the correction I know is some constant. Let me call it alpha sub h. So this is some number, which you can also determine if you care about, but I don't care about right now, times lambda h. So how do I figure out what power of tau I'm going to get? Well, the simplest way to see this is to go back here and look at this. OH has dimension h. Tau has dimension -1. So that tells me this whole thing must be dimensionless. So the dimension of lambda is 1 minus h. Right? Okay. Because then this whole thing is dimension 0. So this is 1 minus h. So the whole thing must be dimensionless because it's compared to a 1. It's just a pure number. So the only thing it can be is tau to the power h minus 1, which is what we have there. OK. So the leading correction to the Green's function will be a series of powers of tau. These are like confluent singularities, as Michael Fisher called them. They come from all these operators which have the following property here, H. Okay. And you can even go to higher orders, but that's the leading term. Okay. Now, similarly, for the entropy, we can make a very similar argument. So the entropy we learned has a leading term that's S0. Now, this S0 is exactly what you'd expect also from scaling. So why is that? Well, you're in 0 plus 1 time dimension. So the energy, or the free energy, the dimension of the free energy, it's an energy. Dimension of the free energy is just 1, because it's 1 over time. And so the dimension of the entropy, which is df dt, and t has dimension 1, is an energy, is 0. So this is a special case where the entropy has dimension 0. So just a number as far of temperature goes. And temperature, of course, you can also put dimension of T. The temperature is just 1, because it's just the inverse of a time. Once you fix this and say this is your rescaling, then this is fixed. This is also fixed. It's all 1. Okay. So now you may know that at higher dimensional at critical points, there's a universal correction to the entropy or the free energy, which some universal number, some power of temperature. So here the power of temperature can only be 0, and that kind of very in a hand-waving way explains why we got a universal number here. This S0 is very analogous to this Fisher-Dijen term in the finite size correction to the free energy of a critical system at its critical point. Yeah, so what Fisher and Dijen showed if you take like the 3D Ising model and look at its free energy at its critical point, so this is in d space-time dimensions, right at its critical point in a finite system, you look at the density, take a finite system of dimension L by L by L. So there's a leading term which is non-universal, but there's a correction which is some number, we'll call it C, over L to the d. So this number C is universal. So this was just pointed out about Fisher and Dijen. This becomes analogous to the central charge in 1 plus 1 dimension. And this number C, this universal number C, is very much the analog of this universal number S0 here. And it's just a number here because of this special case in 1 dimension. Okay. So that's a long saga. So similarly, exactly like this, now I can say that the S of t is S0 times 1 plus sum on h, lambda sub h. And then I have to make this dimensionless. And so this is a function of temperature. Temperature has dimension 1. And so lambda h has dimension 1 minus h. So this should be h minus 1. Okay, so there's a lot of things I can then deduce very generally from this kind of conformal perturbation theory. This is very general, applies in all kinds of conformal field theories. But now the special thing is I need the values of h. What are these h? They are a set of numbers. And each conformal field theory has a set of numbers h associated with it. For the Ising model, the spin operator has dimension 1/6, and the energy operator has dimension 1/2, if I remember right. Anyway, so what are these numbers here? So it turns out to be quite a simple argument that I learned of from Igor Klebanov, actually, that allows you to get these numbers. So what we're going to do is actually compute a 3-point function. We're going to compute a 3-point function, which is right here, in the large n limit, okay? So or you can say we're going to just solve for the vertex operator. Let's do it over here. Okay, so we're just going to take let's just call an operator O. For now, it's psi bar psi, or psi dagger psi. And we're just going to compute the O operator here with this object. So this is going to be a 3-point correlation function. You insert a psi bar psi here, you insert O here, and you compute this exactly. That's just giving you this. And there's another psi here and a psi dagger here. Let me make it a dagger. Okay. So say I wanted to compute this, where O was just, say, the ordinary fermion bilinear or anything else like it. Well, in the large N limit, if you do the large N limit in powers of Jij, which you can do by just drawing diagrams and averaging them, this turns out to be just a very simple equation. So if you try to compute this, you'll find that this is the leading correction. And so on. And in fact, you get an infinite set of ladder diagrams. And all other terms are down by factors of 1 over n. So this is not that difficult to show. You just start with the original SYK Hamiltonian, just expand it in powers of UIJKL. You average the terms order by order, and you'll see that the only terms that contribute are this set of ladder diagrams. Okay? So if I want to compute this correlation function, which is this object right here, I just have to sum this ladder diagram. Okay? And what will happen? What do I expect this correlation function to look like? Well, so here we use an idea which, well, let's see. What do we expect this to look like? Well, in general, it's very complicated. But, yeah, maybe yes. Do I need to introduce the operator product expansion? No, I won't do that. Okay. Yeah, okay, maybe I should do it. So this operator O, we're going to think of as, again, some sum over this, over these other operator OH that I added in the action. So some lambda tilde of H times OH. Okay, so when I insert this in here, what I'll find is that this is going to be equal to sum over H of O sub H psi psi with some constants out front. And the point is that once I put in a scaling operator here, this has a pure power law decay. So this is a very complicated function of the 3 times. So the Green's function was much simpler. It was only a function of 1 time, 2 times or 1 time difference. And we found that the Green's function can be written as the sum of various infinite number of power laws over here, multiplying the leading term. So a similar thing was going to happen here. You're going to get a sum of an infinite number of power laws. And really, if you want to solve this, you can just put this equation on a computer and try to solve it. You'll have to pick out all those power laws. And once you picked out the power laws, you will have an answer for what the values of H are. Okay? So this graph here defines an integral equation, which is written down on the next slide. So another way to rewrite this equation here is in this way. So this is an integral equation for this operator O. And so if I just pick out the OH term, before I go there, okay. Then this is what the equation looks like. You have the 3-point vertex, and this kernel times V is this term right here. So now I have to tell you why I'm going to drop the leading term. Okay. All right, so you got this integral equation. You put it on a computer. Then you take these 2 times and take them far away, and you find some power law decay. And from those power laws, you'll pick up what the values of H are. That's too tall a task. We don't want to do it. Remarkably, you can actually solve the problem exactly, analytically, at least in terms of determining the values of h. And the answer goes something like this. So, we are interested in the case where we want to put in a source here in a clever way. We want to put a source here in a clever way so that you don't get a sum over infinite number of power laws. You just get one power law. Now, that will happen when, say, these corrections start dominating this term. So let's assume this term here is much, much larger than the bare term. The bare term has some bare scaling dimension. It gives you, basically, it's under UV, it's going to scale to 0. Under RG, it's going to scale to 0. And so you don't worry about the bare term. You're only interested in the term that arises from the non-trivial interactions. So you throw out the bare term, and you put an E here, which is, of course, just 1. But the reason I put an E here, because now this equation has the form of an eigenvalue equation. So I can rewrite this equation out over here. That's done over here. So V sub h is when you have a scaling operator, I assume that I can throw out the leading term. So I have this 3-point function, which I don't know. And then this V is the solution of this integral equation. It's an eigenvalue equation. I need to determine the eigenvalue V for energy E equals 1, eigenvector V, excuse me, for energy E equals 1. And this K, which is the kernel, that I know. What is the kernel? Well, the kernel is just this little piece of the diagram. So let's see, it's this tau 3 minus tau 4, and tau 4 minus tau 3, and tau 3 minus tau 1, and tau 4 minus tau 2. Okay, so it's this quantity here, and you get a factor of u squared because there are two interactions, one here and one here. Now, magically, one thing that happens is that the u's cancel out, because the g's, you may remember, go as 1 over square root of u, and so the u's cancel out, all those, and it just becomes a pure number. So you have this integral equation. So g, it's this very complicated function because you know g star. You put it in here, and now you've asked your mathematical friends to solve this eigenvalue equation. This is what you have to do. Find all values of h for which you can solve this equation. Okay. Magically. Yeah, so I'm coming to that. Okay. So you can try to solve this equation, and for general tau 1, tau 2, tau 0, and so on. But let's assume that, let's simplify life. It can, in fact, can be done. The exact form of V is in our review article, actually, I think. The exact solution of this is known. But let's just try to get we are not interested in V, let's say, we are only interested in values of h. Okay, so let's take tau 0 to infinity, so that everything becomes only a function of tau 1 minus tau 2. So that simplifies your life, because you only have a function of a single time here, which is tau 1 minus tau 2. All right, so V, we remember, is basically this 3-point correlator. V is, again, and we just look at it using dimension, has an O and a psi and a psi. So what is the dimension of O? That's h. Dimension of psi is 1/4. And if I've got this right, why is that a minus h? Okay, now I'm lost. I think maybe you're truncating the external legs. Let me see if I remember this right. Okay, so the h, does h come out right? No, the h comes out in the wrong place. Dimension of O is h, so it should be tau to the h over here. And the 1/2 comes from the two sides, so that should be plus h. Maybe I've made a mistake, yeah. All right, I will correct that next time. Luckily, I have another lecture where you can make me honest. So that may be plus h. I think that's probably plus h over there. Okay, so you make an ansatz for V. You look for an eigenvector of this form. Okay. So just a power law decay as tau 0 goes to infinity. So assume there's an eigenvector which is just a power law. We don't know the power law, but you know K, and now this is just a power law. You plug into this equation and just do the integrals. Okay, and all the integrals can be done. The answers are finite, and you get an equation for E, which only depends on H because U has canceled out. And this equation, I believe, is correct. This is what you get after some pages of algebra. So that is the equation for H. So this, now you get a transcendental equation, transcendental values for H, which you have to solve by solving this equation. And so these are the solutions. So the leading solution is H equals 2. And everything else, all the other values of H are positive and larger. There's an infinite set of them. The next one is 3.77354, and so on. These are just solutions of this equation. Okay.
No, I think this equation is okay because C dagger C is like 1 over 12 of tau.
Yes.
And OH is like 1 over tau to the H, and it's 1 over tau to the half times.
H, yeah, it's really plus H, I think, but I may be mistaken somewhere. Yeah, I will correct this by next time. Sorry about that. Anyway, so the leading value, so we only, for the rest of this lecture, we only care about the H equals 2 value, okay? And so there it is. That's the linear in T correction, which is right here. You put H equals 2, so the leading correction is linear in T. So you notice this is a correction to scaling. It comes from adding an operator. So the dimension of the operator is 2. And in terms of RG, this coupling lambda, d lambda h dl, the dimension of lambda is 1 minus h, is 1 minus h times lambda. So all these h's are greater than 1. That's a necessary condition. If any of the h's had been less than 1, forget it. Go back to the drawing board. You have a relevant perturbation. But they're all irrelevant. They flow to 0. And it gives you a correction to the entropy, which is also subdominant at low temperatures. So this you can also see from here. If H was less than 1, this correction would diverge. So it can't do that. And so H has to be greater than 1. And there happens to be, it seems like an accident, a solution with exactly H equals 2. All the other values are transcendental, but there's one value which is protected. It's exactly 2. All right. Yes?
So those you get by solving the thermal equation of that. So you're doing conformal perturbation theory in the IRCFT itself.
Correct.
But presumably as you go to higher temperatures, you get corrections to that thermal equations, right? That come from connecting the ion theory to the UV.
All of those UV effects are absorbed into the values of these coefficients. To actually get the values of these coefficients here, I need the full theory, and the UV will matter, but it won't change the values of H. So, the moment I threw out the bare term, the UV term is this term here. The moment I throw this out, I've essentially gone to the scaling limit. And I'm only looking at the eigenvector, scaling eigenvectors.
I guess what I'm trying to ask is how many of these corrections can you actually trust in the full numerical problem? So you've got the first linear in T corrections, then you've got these higher powers of T.
Yeah.
But once you connect back to the UV theory, you get non-universal.
Well, there is non-universal terms here. All these lambda h are all non-universal. They depend on, the lambda depends entirely on u and everything else. If you took a slightly different model, they'll be different.
But you couldn't get any different powers of temperatures that wouldn't be captured in the thermal equation that you wrote for the IRC.
This is the low temperature expansion.
Yeah.
Okay. This is the structure of the low temperature expansion. It doesn't tell us what happens is, this is just the, all the non-analytic terms at 0 temperature we are identifying. There could be terms that are, of course, non-perturbative terms in temperature, which will change the results at higher temperature. We can't say anything about higher temperature, right? There's another caveat, which is, I don't think the point you're making. It turns out that this operator H, this operator H equals 2, it seems irrelevant here, but eventually it does become very important. But that only happens when your temperature becomes so low or your times become so large at the order n. So this actually breaks down. So this whole approach breaks down. Or let's say H equals 2 operator is dangerous when the temperature or the temperature is very low, when temperature is smaller than U over n. So we've sent n to infinity, so we don't care about that. But if you do care about it, then this is very important. And this turns out to be important for black holes considerations. Now, so another thing, when you first see this, you say, well, n is infinity, that's the thermodynamic limit. Why should I care about such low temperatures? Normally, you think, a system with quasiparticles, the energy level spacing is 1 over n, so when you're hitting 1 over n, forget it, even thermodynamics doesn't make any sense. But not true. Here, this energy level spacing is e to the minus n. So this is still a pretty large temperature compared to e to the minus n. There's a huge window between 1 over n and e to the minus n, and that's where you can't do this perturbation expansion. Okay. This breaks down at temperature of order 1 over n, but you can go all the way down to e minus n, and that's also now well understood for this model, what happens all the way down to e minus n, and I'll try to show you how that proceeds. Okay. But all of the other operators probably don't make any difference, as far as we know, to these very low temperature considerations. But they do become important at slightly higher temperatures. When temperatures of order U, U over 10, then you forget about those. You can just treat all of these operators as irrelevant. Okay. All right, so the rest of the lecture, and maybe the next one, I suppose, the way I'm going, is to just treat this special operator of H equals 2. We found this special operator, which is the most important, the leading irrelevant operator in the large n limit, and now we want to understand it a bit better. In particular, we want to understand why is there an H equals 2 to begin with? Why did I get only one rational value and everything else being transcendental? Okay. So that's what the Schwarzian theory is. It's a way of accounting for this H equals 2 operator, not just perturbatively. We have to take the special operator of H equals 2 and really do it to all orders. And in fact, that can be done exactly as shown by Witten and Stanford. All the nonlinear corrections due to the H equals 2 operator can be accounted for. And so the words used by Kitev and So, they call this the operator the time parameterization soft mode. And it's in condensed matter language, it's a dangerously irrelevant operator when your temperature becomes of order 1 over n. But above 1 over n, it's not dangerous. It's completely irrelevant. Well, not completely, but it's the leading term that will give you the specific heat. In that sense, it's important even for condensed matter, depending on your application, of course. All right, so now let me show you the derivation of the action for this special operator to all orders. The H equals 2 operator, we're going to ignore everything else. All right, so here we proceed with the replica approach that Antoine just outlined for the free fermion model. You go along the same route here, but for the interacting fermion SYK model. Okay. All right, but the one advantage is here, we're not going to be interested in the spin glass phase. And so we just ignore the replicas. We just go ahead and compute the average of the partition function and just ignore the replica index. It doesn't play any role as long as you're not in the spin glass phase. Okay, so maybe I don't want to write down all the steps. So you take the original SYK model, and you just take an average. So let me just at least schematically indicate here. You have integral d tau of u I j k l of c dagger I, I'm sorry, I've switched to c rather than psi, c k c l. You do an average over uij, and when you do that, you'll get a u squared fem c dagger c to the power 4. And that's what's written over here. Here, in fact, the replica indices are still alive. So this is an exact representation of the average path integral. All right, so now a very convenient way to proceed is to introduce unity by the following identity. So if I do the integral over sigma, and I assume that there's an I here which is absorbed in the contour for sigma, this is just a delta function. It's a delta function that tells me G is minus 1 over n c times c dagger. It's just the operator identity between G and this. So that's why we call it G, because that is exactly the Green's function. At the saddle point, the expectation value of this quantity G of tau 1, tau 2, is now a field, and its expectation value will be the actual Green's function, which will be tau 1 minus tau 2. So that's why we're calling it G. It's a two-time field. It's a bilocal field whose expectation value is the Green's function. Okay, but all right. And then you do the integral over G2, and that gives you 1. Okay, the delta function just gives you 1. All right, so you insert this identity here. And now, of course, the point is, since G is exactly this, that's as an operator identity, I can replace this object here by G to the power 4. And once you do that, then the integral over the fermions becomes completely quadratic. Okay, so what you see then is you have c dagger times this minus mu times c, and then you have sigma times c. And now this tells you why you call this sigma 2, because that's, again, it's a field whose expectation value is the self-energy. But again, it's a bilocal field. All right, so you do the integral over c after inserting this identity, then you get an exact representation of the average partition function of the SYK model. So initially, we had a path integral over n fields, n fermion fields, which are functions of time. We've reduced that path integral to path integral of 2 fields, g and sigma, which are functions of 2 times. So 2 bilocal fields, and there's an action, and this is the exact action without approximation. So this log det comes from doing the path integral over the c's. The sigma times g term here is just this term right here. And then this term here, which is the action part of it, gives you g to the power 4. You could have also done this for the random matrix model that Antoine just talked about this morning. You would have got exactly the same expression. Well, this will be replaced by t, and this will be g times g, not g squared times g squared. Everything else will be the same. Okay. All right, now if you take this action and now do the saddle point equation, you solve the equation ds d sigma, ds dg is equal to 0, and ds d sigma is equal to 0. You will get the SYK equations, which Antoine also wrote up. G is omega plus mu minus sigma, and sigma is g cubed, something like that. Sorry. Oh. All right. Okay, so this is so far exact. And we can take a saddle point and solve those equations and look at all their beautiful properties, all of which Antoine has already described for you. What we want to do is do a bit more here. We want to do the path integral. That's an impossible task over the full fields G and sigma. But can we do the path integral a little bit better at low temperatures? Okay. All right, so here we're going to use a method which is very familiar to us. We're going to use symmetries. So, and in particular, you may have heard something called the nonlinear sigma model. So suppose I have a ferromagnet, which is described by some 5-4 field theory, and you're in the ferromagnetic phase, and you want to understand the low temperature properties of the ferromagnetic phase. So, say all the spins point in some direction in the ferromagnet. So if you want to understand the low temperature properties, you know that your low energy excitation are spin waves. So you write down what you say that I'm not going to integrate over all possible fluctuations of the spins. I'm only going to integrate over fluctuations of the spins that rotate the antiferromagnet. Okay, so a ferromagnet. So, and that gives you the sigma model. Okay, so let me write this down here actually. How am I doing on time? I'm out of time. Okay. Okay, I won't go forward this, but let me at least recall for you the ferromagnet and I'll stop. So suppose I have a ferromagnet, let's say a classical system. So I have some grad phi squared minus u minus r phi squared plus u phi to the fourth. But let me also add a very small term, which is like a field, say that's pointing in the z direction. Well, this is mostly zero, very small, and this is full rotationally invariant. And then, I'm instructed to do this path integral of something like this. But I'm in the low temperature phase, so what am I going to do? Well, I'm going to say is that my phi is going to be some phi 0, let's say it's 0, 0, 1. And I'm not going to allow for all kinds of angular fluctuations. I'm just going to have some rotation matrix, O3 rotation matrix that acts on this. And this is going to be a function of x. And then I'm going to put this in here and derive the nonlinear sigma model. So the Lagrangian of the nonlinear sigma model will be something like the gradient of the rotation matrix that will come from this gradient term. And then a small anisotropy here, which will give me h times the z component of this thing. Say r in the z component, something like that. So, and you can ignore everything else. So it's the symmetry that tells us, symmetry of this problem tells us that you're dominated by just the terms in the path integral that take you along equal energy states, where this thing doesn't change in energy because all you're doing is rotating. At least these two terms don't change. There's a gradient term that gives you some gradient cost. So here we're going to do exactly the same thing, except the symmetry here is not as simple as rotations. It's time reparameterizations. We've already seen from Antoine's lectures that the saddle point equations and also the action itself, provided you ignore this term here, is invariant under this symmetry. So what we have to do is to take this time reparameterization symmetry and do a path integral over all possible time reparameterizations. And symmetry arguments tell us that path integral gives you a certain action, which I'll write down next time. Okay.